Good morning, everyone. Today we are going to introduce a new topic called linear programming. It is actually a mathematical technique used for optimization of a problem. See, linear programming is also known as it is a linear optimization. It is a mathematical method for determining the optimal allocation of limited resources to achieve a specific objective. Most of the practicals, we are facing this particular problem, that is, our resources are very limited and we want to optimize the allocation of these scarce resources. And it is widely used in mathematical modeling techniques to determine the optimum allocation of scarce resources. And resources are typically include, it may be raw materials, or maybe manpowers, or maybe machinery, time, cost, money, space, etc. So the technique is very powerful and found especially very useful because of its application in many different types of real business problems in the areas like finance, production, sales, distribution, personals, marketing, and many more areas of management and economics. See, as its name it implies that the linear programming consists of linear objectives and the set of linear constraints, which means that the variables in a model have the proportionate relationship. It deals with the problems where both objective function and the constraint that are linear in nature. And in simple terms, we can say that the linear programming problem is a set of linear equations that are used to find the value of variable to optimize the objective function. So here, the primary goal of the linear programming is to maximize or minimize a linear objective function subjected to a set of linear equality and inequality constraints. So in that particular way, that is linear programming problem, we are trying to optimize in the sense that it may be either in the form of maximization or minimization of a particular objective. Now, it is a process which take into the consideration of certain linear relationship to obtain the best possible solution to a mathematical model. See here, it is a mathematical device. It is applied to those problems which require the solution of maximization or minimization of a problem subjected to the system of linear inequalities. And these linear inequalities which are stated in terms of certain variables. So that is the optimization problems like a maximization of profit, especially in economics, minimization of cost, or minimal usage of resources, etc. So all these optimization problems are the general examples of the linear programming problem. And see here, the linear programming is helpful in developing and solving a decision-making problems. That's why it is optimized either in the form of maximization or maybe in the form of minimization by using a particular mathematical techniques. And this techniques is popularly known as it is linear programming. Now, if you look at the history of linear programming, see, the linear programming technique was firstly introduced by a Russian mathematician, L. Kantorovich, and he was formulated the first problem in linear programming which was popularly known as a transportation problem. Later, in 1945, an English economist, George Stigler, describe the another problem by applying the linear programming for determining an optimal diet. Then it was George Bernard Danzig, G.B. Danzig, an American economist. In 1947, he used the linear programming technique for planning the diversified activities of US Air Force connected with the problem of supplies to the force. So he also suggested an efficient popular method which is known as, it is the simplex method, which is an interactive process, or it is a pivoting process, or it is an interacting process to solve any linear programming problem. Then after that, see, the Kandarovich and T.C. Cookmans were awarded the Nobel Prize in Economics in the year of 1975 in economics for their revolutionary work in the linear programming. So nowadays, linear programming is became a widely used techniques in various disciplines such as economics, operational research, engineering, business management to solve optimization problems like profit maximization, minimization of cost, maybe resource allocation, production planning, transportation problems, portfolio optimization, etc. So it provides actually a powerful framework for making efficient decision in the situation where the resources are very limited, or we can say that we have a scarce resources are there, then at that particular point of time we are generally using this type of optimization problem. Now, there are certain characteristics of linear programming problems. See, the first one, all the variables should be linear. See here, the relationship between two or more variables should be linear. The objective function and all the constraints, or it is also known as all the limitations in the linear programming problems, are linear function of a decision variables. Similarly, the decision variables will decide the output. One of the most important thing regarding the linear programming problem that we have to identify the decision variables. And this decision variable means it is a linear programming problem which represent the quantities or actions that the decision makers can control or determine in order to achieve their particular specified objectives. For example, in a production planning problems, decision variables represent how much quantities of different commodities to be produced. Here, the resource allocation problem, it represents how much of each resources is allocated in various activities so as to produce different quantities of commodities. So decision variable is one of the most important thing regarding the linear programming problems. The third one, see, the objective function should be specified quantitatively. That means the objective function in the linear programming problem should be specified quantitatively in terms of, mostly it is in terms of decision variables, which means that the goal or objective that the decision makers seeks to optimize, that is, for example, whether they maximize profit or maybe minimizing the cost or maximizing the efficiency or achieving some other objectives, should possible to express in quantitative terms. This is also another most important features. Then another one, see, constraint define the limitations or the restrictions on the decision variable and the shape of feasible region. We will discuss what actually the feasible region is. See, which is the set of all possible solutions that satisfy those constraints. There may be different solutions are there and that satisfy our constraint. So constraint may be expressed both in equalities or maybe in terms of inequalities. Mathematically, they take the form of linear equation or inequalities involving the decision variable. Now the another most important characteristic of linear programming problem, that is non-negativity of variables. That means variables should always be a non-negative or zero. So here this assumption says that the decision variable cannot take a negative value. They must be greater than or equal to 0. Mathematically we can say that the decision variable, for example, we have a xi is greater than or equal to 0. That means it is non-negativity constraint that can be expressed, that is the variable, decision variable, that is xi is greater than or equal to 0 and it cannot be negative. Now another most important feature, the decision makers are rational. The decision makers should behave in a rationally. That is also one of the important assumptions. See, in a linear programming problem, we assume that the decision makers are the rational actors who seeks to optimize their objectives. It means that they will choose most favorable solution among all the feasible solution, among all feasible alternative solutions. All feasible solution means that particular solution that satisfy the constraints. So among that particular feasible solution, the decision makers should choose a particular option that should be an optimal. In that way, we can say that decision makers are the rational. Another most important characteristic of linear programming problem is optimality. See, linear programming problem seeks to find the best possible solution, either in the form of maximization or maybe in the form of minimization of a particular function or particular objective. Among all the feasible solutions, the decision makers try to select the best possible solution. And this solution is generally known as it is optimal solution. That is, here it is concept of optimality will become. So it will be an optimal solution. There will be only one optimal solution among the various feasible solutions. So linear programming problem is actually trying to find out the best solution to the optimization problem defined by the objective function that satisfy the various constraints. So understanding these various features, it is very important, especially for formulating and solving linear programming problem effectively and efficiently. Now we are going to express the mathematical format of linear programming models. See, in order to frame a linear programming model in a mathematical format, certain concepts and steps are involved, which is to be very clear in order to frame a particular linear programming problem. So here we have to identify various decision variables. Then after that, we have to frame an objective of the function. Objective function we have to finalize. After that, we have to identify what are the various constraints in the given problem. Then we have to say that all the given decision variables are non-negative. We will discuss one by one in detail. The first one is decision variable. As I have already explained what actually the decision variable means. See, these variables describe the quantities or action that the decision makers can influence or they want to determine to achieve a certain specified objectives. And these variables are building blocks of the linear programming problem, because as they directly influence the optimal outcome or the optimal solution. So these variables are generally denoted in terms of, say, x1, x2 or maybe x3, or it may be xyz and so on. And the production, for example, in a production planning related problems, see, the decision variables are mainly represented in terms of the quantities of different commodities that producer wants to produce. So that will become the decision variable here. For instance, see, x1 may represent the number of unit of commodity that producer need to produce. Similarly, x2 may be another decision variable which maybe represents, See the number of unit of commodity that producer want to produce. So like that we can introduce many decision variable depending upon the nature of given problem. So in most of the practical problems, see linear programming problems involves multiple decision variables, and which means that two or more decision variables are generally involved in the linear programming problem. So the first step is we have to identify the decision variables. After identifying decision variable, we have to specify our objective function. See, every linear programming problem has an objective function. And the objective function in linear programming problem is the goal, or it is the objective that the decision makers aims to optimize. So it may be the maximization or maybe the minimization of any particular objective. For example, in the case of a maximization objective, the decision makers seeks to maximize some measures of performance. For example, it may be a profit maximization, or it may be a revenue maximization, or it may be utility maximization, like that. See, while the minimization is generally seeks to minimize some of the measures of cost. For example, it may be in terms of cost of production, or maybe some sort of distance, or maybe time requirement that we want to minimize. So in the objective function in a linear form, these are generally expressed in a linear form, which means that the mathematical expression of the objective function generally in the form of a1 x1 plus a2 x2 plus a3 x3 plus up to an xn. See here, a1, a2, a3 are the coefficient of the variable x1, x2 and x3, and it represents a linear combination of decision variables where each variable is multiplied by each variable, that is for example here x1, x2, x3 are multiplied by their corresponding coefficient, that is a1, a2, a3 up to an. So the objective function is generally expressed in a linear because the sum of these linear terms are generally expressed. So the coefficient of the decision variables in the objective function represents actually what are the contribution of each variable to the overall objective. So these coefficients can be either positive, which indicating that the increasing the variable will lead to the increasing objective function, or it may be negative, which indicating that increasing variable will decrease the objective function. It have different directions. Okay. So depending upon whether the objective function is maximized or minimized, this function might be followed by either the maximize or minimize. For example, if you want to maximize the profit, then here the variable x1, x2 and x3 represent the quantity of different output or the quantity of different commodities, and a1, a2, a3 represent the profit per unit of each product, and the objective function generally look like will be see maximize a1 x1 plus a2 x2 plus a3 x3. So this objective function represents the total profit is obtained by selling the quantities of x1, x2, x3 products of commodity 1, 2 and 3 respectively, and which their corresponding profit rate will be. See, it will be a1, a2 and a3. So this is the objective function. See, after specifying your objective function, we have to identify what are the constraints in the given problem. See, every objective function in the linear programming is subjected to these certain limitations, or we can say that these limitations are generally known as constraints. So the constraints in the linear programming means these are the limitations or maybe the restrictions on the decision variables like x1, x2, and these restrictions may be in the form of limitations of raw materials, limitations in terms of time, maybe in terms of money, or maybe in terms of equipment is maybe limited. For example, suppose we want to maximize consumer utility or satisfaction from the consuming two commodities. In this particular case, the constraints may be the budget of a consumer. The budget of the consumer is limited with the given price of the commodities. So in this case, it represents the condition that must be satisfied in order to obtain various feasible solutions. So constraints are generally expressed. See, it can be expressed in terms of equation or maybe in terms of inequalities involving various decision variables. So for example here, we have a1 x1 plus a2 x2 plus up to an xn, which is less than or equal to a particular constant. This C will be the constraint. Similarly, we can also write the same constraint in terms of equal to a particular limitation. So in this particular way, we can define the constraint. See, after defining or specifying your constraint, then next step is non-negativity restrictions, or we can also say that it is non-negativity constraint. See, the constraints are essential aspects of a linear programming problem. Here, the non-negativity constraint, we are considering that, which is also important, and these constraints impose certain conditions on the decision variable. See, we are here specifying that they cannot take any particular negative values. So instead, they must be equal to or greater than 0. Mathematically, we can say that a decision variable, for example, we have an xi, then the non-negativity constraint can be expressed, see, xi should be greater than or equal to 0. Why we are taking this non-negativity constraint? Because in many real world scenario, see, that are modeled using linear programming problem, negative values for the decision variables may not make any particular sense. For instance, see, the quantities of items produced or the resources are allocated or the distance you are going to travel, that cannot be negative. If it is negative, then we are unable to interpret it properly. For example, if these values are negative, then how can we able to interpret the model correctly? So that's why we are assuming that our variables are non-negative, that means it is greater than or equal to 0. So by considering all these aspects, see, we will have a mathematical expression of linear programming. See, it will be similar to, see, maximize, for example, here it is, I am denoting Z for the profit. So maximization of profit is my objective. That is a1 x1 plus a2 x2 plus a3 x3, which is subjected to different linear constraints. That is, for example, a1 x1 plus a2 x2 plus up to an xn, which is less than or greater than c. Depending upon the constraint, it may be less than or equal to, or it may be greater than or equal to, depending upon whether you want to optimize the maximization or minimization. Depending upon its sign will also change. I will discuss it at the later stage. Then the a1 x1 plus a2 x2, which is up to an xn, we have less than c. We have number of constraints depending upon the number of variables we have. So accordingly, we have an xn plus an xn up to an xn where it is less than equal to c. So these are non-negativity constraint. We are assuming that x1, x2 and xn up to xn variable are greater than or equal to 0. So after finalizing the mathematical expression, see, we are considering some of the terms which is generally used in linear programming problem. One is feasible solution. What do you mean by a feasible solution? See, feasible solution refers to the set of values for the decision variables that satisfy all the constraints of the problem. As I have already told you, we may have different types of limitations which are generally known as it is constraint. But if the constraint and satisfied, they may have number of solutions that satisfy our constraint. So these solutions lies within the feasible region. That means all are achievable, which are the set of all possible combinations of decision values that satisfy the constraint. So it means that the values of decision variables must make each constraint equation or inequation is true. That means that are satisfied. So we may have the several feasible solutions to the problem. However, feasible solution is not necessarily optimize the objective function. In order to optimize, there will be one among the feasible solution may be considered as an optimal solution. So that's why we are saying that feasible solution do not guarantee an optimal solution. Rather, they are simply the solution that are valid within the framework of the given problem's constraints. So we may have number of feasible solutions. Among the number of feasible solutions, we may have one optimal solution. See, the optimal solution is nothing but it is the best solution or best possible solution that achieves the objective function. That may be maximization or minimum value that satisfy all the constraints. So it is the solution for the optimization performance measures defined by the objective function. So it is the best among the all feasible solution. So the nature of optimal solution entirely depending upon whether the objective function you want to maximize or minimize certain performance measures. For example, in the case of a maximization problem, see, the optimal solution represents the highest achievable value among the different feasible solution. So we can say that the maximization problem, the highest achievable value of the objective function within the feasible region will be considered as an optimal solution. Similarly, if your problem is related to the minimization problem, see, then the optimal solution will be considered as the lowest achievable value. It will be lowest achievable value. So in this way, we can define the feasible solution and optimal solution. The examples we will discuss in the upcoming classes. So let me conclude here. Today we have introduced the concept of linear programming, its history, and various features and related concepts of linear programming, like what is the decision making variable, what are the objective function, constraints, non-negativity of the variables, feasible solution, and the optimal solutions. So in the next lecture, we will discuss the detailed analysis of how to formulate a linear programming problem. So we'll see in the next lecture. Thank you.